Thank
Was he
you.
lying in the grass?
I'm sorry? Don't try to figure it out, Max. Your head works.
Hey, he's Harvard.
He's going to Harvard.
He is.
I knew this would happen if I would.
Yeah. Did you apply yet? What are you going to study there? Well, how can you get in if you don't apply? What do you think, you're Kanye? Come on, that was pretty good. Does anyone have any idea what I'm talking? Do I have to explain everything to you people? Kanye said he wouldn't go to the Grammys unless they guaranteed him an award that he wasn't nominated for. Oh, God. That was funny. So Max was going to go to Harvard even though he didn't apply. So is he, oh.
Wait, explain the dark.
Stop talking. All right, we're going to talk about the Pert equation. You've used the Pert equation. The Pert equation was given to you like magic. Hey, here's this cool formula. Go use it. And you did. Oh boy.
You missed him.
I didn't get the Pert equation, so can you write that on the board for me?
Yeah, I did. It's right there.
Or is it on the slideshow?
It is on the slideshow. It's right there.
No, like,
we haven't learned it yet.
Dude, you haven't learned it yet.
all right, okay. Because I thought you said understand the Pert equation, so that I meant that you guys ready.
Yeah,
I
after
smell
the
Harvard
lesson.
just around the corner. I'm sure that one you got.
Can I leave now?
Yeah, you can. This is America. So you've been given the Pert equation last year in pre-calc. You solved a bunch of problems with it. You did some financial stuff. You did growth and decay. We're gonna revisit all of that again. The difference is we're gonna talk about where that Pert equation comes from, because you need calculus to come up with this equation. So last year it was like magic. Here, go work with this. And this year it's not so much magic. So we're gonna derive the Pert equation and show you. We're gonna start from scratch, derive it, and then answer questions about it. And then we're going to skip that one because obviously nobody's being nice to me today. So, Pert equation. All right.
Do you have notes on reading?
It depends, whatever you want to do. I mean, if you want to just take notes on the sheet I gave you. The reason I gave you the sheet is because the problems are already written out, so you don't have to spend 20 minutes writing like a mad person trying to copy the problems down. We will get to the problems right away, so there's probably room on that page where you just need to write this down.
Thank you.
The Pert equation that you learned a while ago is in that form, and sometimes this P is changed. Maybe it's an A if you're talking about money. P is your starting amount. R is what? Rate. Okay. Expressed as a decimal, not a percent. T is time. E is, anybody?
E?
E is
2.7181.
1828818284590.
Well done, Claire. Let's give it up to Claire. We're going to look at a couple variations here. We might change the P to a C. We might change the R to a K. But this one, the dy over dt equals cy, is where we're going to spend most of our time. It will make more sense as we work through some examples. So let's start with the bacteria example, okay? Which is, I believe, the first one on your note sheet. Yep. All right, so we got some bacteria. It grows exponentially, as do many diseases, or germs, or bacteria. I'm assuming you can read all those big words. However, there are a couple words in there that we're going to need to emphasize. First one is the rate of increase. The second one is directly proportional. And the other one is the number of bacteria. Okay, so we need some variables. What do you want to call the number of bacteria? B would be a great number. B stands for bacteria. Excellent point. Let me start over. What variable would you like to assign to bacteria?
B.
B, good call. So I identified my variable. T is time. You're pretty much safe. You don't have to explain that because I think we all assume that that is in fact what T stands for. And we have to put that sentence into an equation. Assuming the rate of increase How would I express the rate of increase of the number of bacteria? Basic.
The number of bacteria over time, so the change in bacteria over 2 hours.
Forget about that. That comes later. We just want a general equation to start.
So delta B.
Good, but this is calculus, so we're going to use dB over dt, which should look familiar to you, yes?
Yep.
Okay, good. The rate of increase is directly proportional to, so we need a proportionality constant. The common letter that we'll use for that is K. You might see some problems where it uses C as the proportionality constant or an alpha or whatever. Is directly proportional to the number of bacteria present. Well, the number of bacteria is B. There's our starting equation. Easy? Beautiful. Now we bring a little bit of calculus to the party. I would like to come up with an equation for the number of bacteria. That's not the number of bacteria, that's the rate of increase of the number of bacteria. So I have to do a little bit of calculus. What's the first thing I do when I'm trying to simplify a differential equation? Yeah. Separate the differentials. dB is equal to kb dt. That's a problem because I have b's on one side, or the b on one side, and the dB on the other side. So I got to get the b to the other side. 1 over b dB is equal to k dt. We could take the k with us if we want, but I'll leave it over on that side with the t. All right, what next?
Is there a reason why you leave the K?
No, just because it's just a standard, just like the reason why we only put the c on the one side and not 2 c's. Roy, do next.
The integral.
Take the integral. Let's start with the easy one. What's the integral of the left side?
Column B.
Do I need the absolute value bars?
No.
Why?
Bacteria can't be, number of bacteria can't be negative.
Can't have a negative number of bacteria, so we don't need the absolute value. That was the easy one. What's the integral of the right side? Nope. 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 TK or KT.
Plus C.
KT plus C. That's why this differential is so important. It tells you what the variable is. The variable is T, not K. Okay. We're working towards a formula for the number of bacteria. Problem is I have the natural log of the bacteria, and I don't want the natural log of the bacteria, so how do I get rid of the natural log?
Raise everything to the E.
Yeah, do the whole e to the trick. What's e raised to the natural log of b? B. And then we got this business. E to the kt. So what we're going to do is we're going to do this. Right? Basic rule of algebra there. If you have the same base and you multiply, you add the exponents. So I just split it into two separate. What's e to the c?
Some constant
C. Good. So this becomes b is equal to c times e to the kt. So our variables change a little bit. Instead of an r, we have a k. Instead of a p, we have a c. So instead of the Pert equation, we have the Kecht equation. But it's the same thing. Okay? There's our general equation. Notice we haven't talked at all about the 600 to 1800 in 2 hours business. We're going to use that for the second part of it. Okay? But I want to make sure everybody understands how I got that general formula. All of this is the calculus involved in deriving that. Notice when we're done, we just have the Pert equation, which was last year, you were just given the Pert equation and you go from this point. We have to find K, we have to find C, and eventually we're going to plug in for T, which would be 4 hours.
When you took the integral for B, why wasn't it like natural log of B plus C?
Because we choose to put the C term only on one side, so we stick it with the non-B term. Okay. Which is why I popped it on the other side. Okay. When we're looking at the Pert equation, that P that you start with is the initial amount. So in this case, what's C?
C is the initial amount.
You can do it one of two ways. You can read the problem and figure it out. C would represent our starting amount. What's our starting amount? 600. Or you can do it mathematically. When T equals 0, we know, so we'll do the little sidebar here. When T equals 0, we know that we have 600 bacteria. So C raised to the E times the K times 0. What's E to the 0? 1, so therefore C is equal to 600. So we start to change our formula here so that the number of bacteria is 600 times E to the KT. Or again, if you're smart enough and you realize we're starting with 600, then you just plug 600 in. Hi.
Hi, Taylor?
Keep your card. Please do it right. How do I find K? What else do we know?
T is 2 hours.
And when T is 2 hours, how much do we end with?
1800.
1800, good. So 1800 is equal to 600 times E to the 2K. Sub in 2 for T, sub in 1800 for B, and solve. Okay, what do we do first to solve that bad boy? Divide by 600. So 3 is equal to E to the 2K. Now what? Natural log of both sides. Natural log of 3 is equal to 2K. Is everybody okay with that step? Natural log of E to the 2K is just 2K. So therefore K is, that's a K, is equal to the natural log of 3 divided by 2, which is approximately equal to, you need your calculators by the way, unless you can do that in your head, good luck. A little bit more.
over.
Well, natural log of 3 would be,
A little over
0.55.
what is it?
0.55.
0.55. Now, because the College Board wants 3 decimal places, this answer should be in 3 decimal places, which is, what's that? 0.549. More importantly, you need to store that number in your calculator. What I would do is I would store it in your calculator for K. Do you all know how to do that? Does anybody not? Okay, beautiful. Store that in the calculator for K, because the College Board is going to expect you to store that number in K and use the exact number, not the decimal equivalent. Because that'll cause problems as we finish the calculation. Yes, Max?
Are they gonna want units on this?
Not yet. Not until we answer the final question. We haven't answered the final question yet.
Sometimes they say that.
I said, but not here. We don't care. Okay, now I'm running out of board space, so I'll jump over here. And we know that the number of bacteria we have is equal to 600 times E to the 0.549 T. And now I can answer 2 questions. One question would be, after X amount of hours, how much bacteria do I have? And if I have X amount of bacteria, how long does it take to generate it? This problem wants to know how much bacteria do I have after 4 hours. Put 4 in for T, plug and chug. And since you stored K in your calculator, you can type in 600 times E to the parentheses K times 4, close parentheses, enter, and we get a value of
5,400.
Can somebody confirm? 5,400 what?
Bacteria.
Bacteria. For those of you that are in AP Bio, bacteria is a plural. What's the singular?
Bacteria.
Bacterium, very good. You have a bacterium, many bacteria. Okay, good? Problems? They get fairly complicated, but you've done from this point on, you did last year, from this point forward, or backwards I should say, that's all new calculus stuff. But still not too bad.
Are we gonna have to like find the formula every time? Like,
Not every time, no. In fact, if I don't get to it, the last slide on tonight's homework, you're gonna do 11 and 12, you're gonna need to derive. The other ones you can start right from the Pert equation. Okay. Can I erase this? Are we good? Let's move on to the next one then. Which is radium. Do you all know what a half-life is? Does it? Anybody?
Yes.
What's a half-life, Mason?
The time it takes for an amount of something to have.
Correct. It's the amount of time it takes for something to, half of something to disappear.
Yeah.
Okay. So if you have a chunk of radium sitting on your desk, it takes a certain amount of time, and over time the radium just magically disappears. The half-life, if you start with 1 gram of radium, it's the amount of time it takes for half of the radium to disappear. The flip side of a half-life would be a doubling time. Doubling time is the amount of time it takes for something to double. Half-life usually has to do, other than a fantastic video game, it has to do with a lot of times radioactive decay, very negative things. Doubling time is usually used in investments. So you invest $1,000. I'd like to know how long is it going to take me to get $2,000 in my account. Okay, but we're going to start with a half-life here. And it has a long half-life, you'll see, 1,600 years for half of that stuff to disappear. Will it ever completely disappear?
No.
Why?
Because we keep having something.
It keeps, right, you keep cutting it in half. So like for instance, Chernobyl, you all know what Chernobyl is, right? Does anybody not? Chernobyl was a nuclear reactor in Russia that melted down and released a ton of radioactivity into the atmosphere and into the local area. So it happened, I think, 19 or 20 years ago. Does anybody know?
30 years ago. We did
Is it that much?
It's
30 years in April, okay.
It's-
They're just starting to go back into the area now because it's so
Well, you can take tours.
saturated.
They
Is that a tour you really want to
They
take?
cleaned up the topsoil, so it's less radioactive than it was before, but it's still really bad.
So as long as you don't like play in the sand, you're okay?
Like the pond.
Yeah. Like Disney World, Chernobyl.
Well, it used to be that the government would have let you go, but now they're loosening up, so you still have to get a ton of permits. It is.
If you really want to, how many people live there?
Count me out.
It was a big-
Don't even bother calling me. Okay, so radium decays exponentially and has a half-life of 1,600 years. Find a formula for the amount of Y remaining from 50 milligrams of pure radium after T years. So we have to get a general formula. We're not going to derive this one. We're just going to start with the equation and see what we get here. Okay, so we'll start with the Pert equation. A is equal to P times E to the RT. What's our starting amount? That'll be when we get to the formula, but in general, what's our starting amount? Do you have any idea? P. What's our ending amount? No.
P sub something.
No. This is the weird thing about half-life. You don't need to know how much you start with. If I start with P and I get to its half-life, how much will I have left? Half of? No. Half of P. So with a half-life problem, we end up with this. What's the first thing I'm going to do to solve that problem? Cancel the P's, or divide both sides by P. Okay. In a doubling problem, instead of a half, you'd have a 2. Okay, now we look and see what do we know. We know that it takes 1,600 years for that to happen. So we know that T is equal to 1,600. 1/2 E to the 1,600 T is equal, E to the 1,600 T is equal to 1/2. How do I solve it?
Wait, it's
Would be 16
We
visual
delivered
bars.
R, right?
You're right, it is, because R, yeah, thank you. R, as you can clearly see. How do I solve that? Natural log. Natural log of 1/2 is equal to 1600 T, R. Let's see who's paying attention, good job. So R is equal to the natural log of 1/2 divided by 1600. Bring that up here, and R is approximately
'Gross.
icky number. Negative 4.32 e to the negative fourth.
Yeah.
Yeah, that's right. Okay, so it's negative 4.332 times 10 to the negative fourth, which we don't really care because you just stored that in your calculator under R because it's the rate.
Doesn't matter what we store it at.
No, you store it wherever you want. So that means we get 1/2 equals e to the negative far point 332 times 10 to the negative fourth t. That was fun. General equation, however, now we go to part A. It says find the formula for the amount of y remaining after 50 milligrams of pure radium after t years. So now we know our starting amount. So we're going to go back to A equals 50 times e to the negative 4.332 times 10 to the negative fourth t. I'm assuming, I should have clarified this, I'm assuming they taught you last year that if your R is negative, it's a decay, and if it's positive, it's a growth. You all knew that, right?
Oh, yeah.
Well, you do now. Question?
What happened to our T? Oh, yeah,
It's right there on the end.
How did you switch from like the 1/2 to the A?
Because I use the 1/2 to find out what R is, but now that I know what R is, I'm moving on to problem A, where it says it gives you the starting amount of 50 milligrams. And now we're going to solve the problem differently. We're going to say, if I start with 50 milligrams, how long will it take to have only 20 milligrams left? Relating this back to Chernobyl, they know how much radioactivity was released 30 years ago, and they know what the safe level for human beings safe level is, so therefore they can do the calculation to figure out how long do you have to wait before humans can move back into the area.
Wouldn't A be 25?
No, because we're starting with 50 milligrams. That's always our starting point. The only thing we use the half-life for is to find out R, and then we forget about it. So 2/5 is equal to e to the negative 4.332 times 10 to the negative fourth t. Now what? Natural log. So we get the natural log of 2/5 is equal to negative 4.332 times 10 to the negative fourth t. So t is equal to this thing, oops, 5, divided by that mess. Which hopefully you stored because you don't, that's not an exact answer. So then, therefore, t is equal to
2,100.
yeah, that's right. 2,115 years.
Wait, oh wait. You just skipped.
No, you should. I just don't have it. What is it? Point.
Wait, oh wait.
Thank you. Okay, now does that answer make sense? Well, think about it. If it takes 1,600 years for half of it to disappear, we had more than half disappear. Therefore, our answer should be bigger than 1,600. It's actually 2,115 years. That's a long time. Question?
Where did, when you said it equal to 20, where did that 20 come in from?
From here.
Oh, okay.
So we stopped here. This is our general equation for part A. So there's A. Then all of this is part B.
Okay.
Then we said now that we have that general equation, we can plug in for any t value or plug in for any a value and work backwards. Okie doke. How are we doing so far? Let's do a law of cooling. You love physics. Oh, I think I just printed something. Let's get rid of that. Let's go back because I didn't want that. Can't work my computer. There we go. Newton's law of cooling. Have you done thermo yet? Who's in AP Physics? Nobody? Did you do what is this stuff?
Yes.
Newton's law of cooling last year? No?
We did cool-
You didn't do thermodynamics?
We did do thermal.
You did.
I'm pretty sure it was Newton's law of cooling. You didn't vote
Wait, you just blanked it out?
Newton's law of something.
Pretty much all.
I mean, how many laws could that guy have written?
I do remember a copy.
He was overrated anyways.
It's not like we're studying.
Just because he did the whole gravity thing and then the cooling and then the calculus stuff. But again,
We did do this.
overachiever, brown nose.
We had full labs on it.
You did full labs on this stuff.
Yes.
We're not gonna do a full lab. We're just gonna do a calculation. Okay. All right, so according to the law of cooling, the rate at which an object cools is directly proportional to the difference in the temperature between the object and the surrounding medium. What's the surrounding medium?
The air. Everything. The air.
The air. We're gonna ignore the cup. You know, you're right. The cup is the surrounding medium, but technically, we're just gonna use the air. If an object cools from 125 degrees to 100 degrees in a half hour, when surrounded by an air temperature of 75 degrees, find the temperature at the end of the next half hour. We're going to derive this one. Okay, so we need a general equation. dy dt is equal to c times y minus. There's my starting equation. Now, where did that come from? The rate at which it cools. Okay, so we're going to call the object temperature y. I probably should have defined that. We'll do it up here. Y equals temp of object. The rate at which the object cools is directly proportional to the difference in the temperature of the object and the surrounding medium. So I choose to use C as my constant. If you don't like C, we can change it to any other variable. You want to go back to K, we can use K. It doesn't matter. Are you okay with C? Are you going to get that C confused with the constant of integration?
Yes.
Okay, so then we'll change it to K. That's not a K. That's a K.
Wait, and the K is from.
Directly proportional.
Okay.
What do I do first? Separate the differentials. dy is equal to k times y minus 75 times dt.
Why did you do y minus 7?
Yeah, where'd you get?
Because it says is directly proportional to the difference in the temperature of the object and the surrounding medium. Since the air is 75 degrees, that's our surrounding medium. The temperature of the object is y, because that's how we define it.
Oh.
It says down here, the air temperature is 75. Okay. I got a dt on the left, I got a dy, no, sorry, I got a dt on the right, I got a dy on the left, I got a y on the left, I need to put that over there. I could distribute the k and do a bunch of other stuff. The easiest thing to do is just divide both sides by y minus 75. So I get 1 over y minus 75 dy is equal to k dt. What next? Integral. All right, what's the integral of y minus 75? Of? Correct. Now I'll give you a warning. You need to do that as a UDU problem. Again, you don't want to get in the habit of 1 over anything, the integral of 1 over anything being the natural log of that anything. It doesn't always work. It has to be done as a UDU. The weird thing here, though, is when we do a UDU, what's a derivative of y minus 75? 1, so it doesn't matter. But again, get in the habit of doing that as a UDU. So we get the natural log of, do we need the absolute value bars?
Yes.
Yes? Why?
It would be less than 75,
It can be?
right?
I don't know.
Oh, yeah, I can, if the liquid's cooler than 75.
Okay, so we'll put it in there and see if we need it later. And the right side?
KT plus C.
KT plus C. Beautiful. Now what? Do the E thing. Okay. What's E to the natural log of the absolute value of this stuff? The stuff. What do we do with the absolute value bars? Do we bring that down? Why not?
Yeah, I would say no as well. Because it's the.
It's gonna get
It's an exponent.
cooler, so it's gonna be less than what it is, right? So it's gonna be a negative number because it's depreciating.
So we want the absolute value bars in there? You don't want them.
I don't know.
Keep them or leave them? Leave them. All right. Are we okay on that last step? I left out a little bit there, but are you okay where that giant C came from? No? Okay, remember, e to the kt plus c is the same thing as e to the kt times e to the c. And e to the c is the same thing as c. So I just took that capital C and put it in there. Okay? That's a pretty common approach.
So on the test purposes, you'd be fine, let's just skip them.
Yep. Okay, what do we know?
Why?
We know why. What's why?
No, we don't know why.
We don't know why?
We don't know.
Yeah, because you're trying to find the temperature.
Oh, we do know that.
You know, it's
Are we agree with 125 to 100?
Yeah, now we're using 125 to 100.
Okay, so who's 125?
What is?
Temperature of the object.
I didn't hear what you said.
The temperature of the object, why?
Y
125.
is 125. When?
At T is 0.
At t equals 0. Okay, so we plug 0 in for t,
Solve for C.
put 125 in for y. 125 minus 75 is equal to c times e to the 0, which is 1. So therefore c is equal to 50. Okay, so what do we know now? The temperature of this thing is 50 degrees. Sorry, no, that's not right. The starting temperature is not 50 degrees. Our C term is 50 degrees. Our starting value is 125. Okay, let me get this mess out of the way. So that means now, oh, that's all right. I can pick up where I left off. Y minus 75 is equal to 50 times e to the kt. Good, I got rid of one of the variables. I figured out what c was. I need to figure out what k is next. How do I do it?
Would we have y equal 100?
We could.
Equals 30?
Not 30.
0.5.
T equals 0.5, because we're working in hours here, I think. Well, you can work it whatever you want. Yeah, half hour. We'll leave it as 0.5. So 100 minus 75 is equal to 50 times e to the 0.5 k. So this is kind of weird. 1/2 is equal to e to the k, or 0.5 k. 0.5 k. Wow, that's horrible. Now what? Natural log. So I'm gonna do something really bad here. Well, it's not really that bad. I'm not gonna get arrested for it, but I combine fractions and decimals. Woohoo. Little help. What's K? Negative
One
1.386.
point three eight six.
Which again, I assume you store. We done? Find the temperature. Okay, so we need to take that and plug it back in. We know what C is. We know what K is. We know what time is. Solve for Y. I'm sorry?
Can you just move 70? Can you move 75?
Is that all of them?
Wait, what?
I'm sorry? Correct, because now it says find the temperature at the end of the next half hour. What? Wait, T is not 0.5 for the last part. What's T? 1, right? Because we know what it is at a half hour. We know it takes a half hour to go down to 100. We want to know after another half hour, what's the temperature? So T would be 1 hour after we started this mess. So you would get Y minus 75 is equal to 50 times e to the negative 1.386 times 1.
Wait, why did you?
What's that?
Oh, because every 1 hour.
We know that after the first half hour it's 100 degrees. We want to know after the next half hour, so that's a total of 1 hour. You know? Anybody have an answer?
87.5.
87.500?
Yeah.
Oh, that worked out nice. Degrees.
Do we have to have the 0, 0?
Nah, you could drop them. By putting them in there, you just demonstrate that you understand they went 3 decimal places, but it's equivalent. You wouldn't lose a point for that one. Can I erase this? Okay, so day 94. Like it says up there, on 11 and 12, I think you have 5 problems tonight, 5 or 6 problems. The only 2 you need to start from the beginning and derive it all the way to the end is 11 and 12. Everything else, you can jump right into the Pert equation. Okay? We're going to wait until tomorrow to go over the 6-1 homework because there's some more 6-1 problems on the homework tonight. It's a combination of 6-1 and 6-2. Put all of today's assignment, 94, on one page. Don't continue the 6-1 stuff on Friday's or Thursday's homework. Do it on a page with all of 94. So that I have one assignment that's got day 90, whatever on it, and then another page with 94 on it. Okie doke? We good? Outstanding.